Astronomers have identified a record-breakingly bright quasar with an extremely voracious black hole at its center. Quasars are compact sources of electromagnetic radiation, a type of active galactic nucleus powered by a supermassive black hole. In a new study, scientists have identified a quasar that is not only the brightest object ever observed, but also contains the fastest-growing black hole. This object absorbs matter with a mass equal to our Sun every day. Quasars are among the brightest objects in the universe. These are a type of galactic nuclei, and their driving force is the supermassive black holes in the center, surrounded by an accretion disk formed by matter falling on them. The black hole itself cannot be observed, but the material in the accretion disk can. Matter falling into a black hole releases gigantic amounts of energy, which manifests itself in the form of extremely intense electromagnetic radiation, covering almost the entire spectrum, from radio waves to high-energy gamma radiation. The brightness of this infalling material can exceed the brightness of the host galaxy by up to 1,000 times. Thanks to this, we are able to observe quasars located at a huge distance from Earth. The distant quasar, designated JO5294351, was initially mistaken for a star, but in fact it turned out to be not only the brightest object of its kind, but also the brightest object ever observed. Moreover, the black hole at its center appears to be the most voracious ever observed. It consumes solar mass gas and dust every day, making it the fastest-growing black hole in history. The description and results of the research were published in the journal, Nature Astronomy. We have discovered the fastest-growing black hole. It has the mass of 17 billion suns and eats just over one sun a day. This makes it the brightest object in the known universe, says Christian Wolf from the Australian National University, ANU, and the lead author of the publication. Quasar JO5294351 is located more than 12 billion light-years from Earth. At its center there is a supermassive black hole. These objects do not emit or reflect light, so they are very difficult to detect. They are so massive that after reaching a certain point, event horizon, the escape velocity, i.e. the speed needed to leave the object's gravitational field, exceeds the speed of light in a vacuum, and even light is unable to leave this area. Astronomers conclude about their presence based on the gravitational effects exerted on the surroundings, i.e. the behavior of stars and matter in their immediate vicinity. However, when the black hole absorbs matter, it is clearly visible. Intense friction and gravity cause this material to heat up to enormous temperatures, shining brightly in space. Astronomers can study this light by tearing it into pieces to learn the properties of the black hole within it. Material from the accretion disk surrounding the black hole in quasar JO5294351 emits so much energy that the quasar itself is more than 500 trillion times brighter than the Sun. All this light comes from a hot accretion disk 7 light-years across. This must be the largest accretion disk in the universe, says co-author of the paper, Dr. Samuel Lai from ANU. For comparison, 7 light-years is about 15,000 times greater distance than the distance from the Sun to the orbit of Neptune. Interestingly, An object referred to as J05294351 appeared in images from ESO's 1980 sky survey, but was considered a star. Automated analysis of data from the European Space Agency's Gaia satellite also recognized the object as a star. Only now has its true nature been discovered. Using the telescope at the Siding Spring Observatory in Australia and the X-shooter spectrograph on the VLT telescope in the Chilean Atacama Desert. Finding quasars requires precise observational data from large areas of the sky. The resulting datasets are so large that researchers often use machine learning models to analyze them and distinguish quasars from other celestial bodies. However, these models are trained on existing data, which limits the search. If the new quasar is brighter than any previously observed, the algorithms may reject it and instead classify it as a star not too distant from Earth. Finding and studying distant supermassive black holes could shed light on some of the mysteries of the early universe, including how these objects and their host galaxies formed and evolved. Ants can navigate using the Earth's magnetic field. They are only a few centimeters long, and their brains have fewer than 1 million neurons and a relatively simple structure. Nevertheless, cataglyphous ants have unique abilities. They can, for example, navigate using the Earth's magnetic field. Desert ants of the genus Cataglyphus can orient themselves using the Earth's magnetic field. Scientists at the Julius Maximilian University of Würzburg in Germany discovered this a few years ago. However, until now it was not known where in their brains this information is processed. Now that has changed. In new research published in the journal Proceedings of the National Academy of Sciences, a team of German scientists manipulated the magnetic field at an early stage of ants' development. This allowed them to determine the regions responsible for processing this information. Ants of the genus Cataglyphus have been the subject of research by scientists from Würzburg for years. In previous work, scientists found that young ants go on what researchers called educational walks. They hang out right at the entrance to the anthill and get to know the area. Before an ant leaves its underground nest for the first time and goes in search of food, it must calibrate its navigation system, explained study co-author Pauline Fleischmann. Ants can go very far from the anthill in search of food. But that doesn't stop them from finding their way back. And it doesn't matter whether they are carrying small prey, in which case they walk forward towards the anthill, or whether the piece of food they find is larger than themselves and they have to drag it, then they walk backwards towards the anthill. Ants do not get lost regardless of how their body is oriented in space. In field studies in southern Greece, scientists from the University of Julius Maximilian wanted to find out which areas of the brain are involved in this process. To do this, they began manipulating the magnetic field near the anthill they were studying while young ants were taking educational walks. In the next step, the researchers looked for changes in their nervous systems caused by disturbances in the magnetic field as an expression of newly acquired experience. During these educational walks, ants explore the immediate surroundings around the entrance to the anthill. They rotate around each other repeatedly, with short pauses between rotations. During these breaks, they always look directly towards the entrance to the nest, even if they cannot see the tiny hole in the ground. The researchers focused on young worker bees that had not yet undergone any educational walks. Animals could go on expeditions only as part of carefully planned experiments, sometimes in natural conditions, sometimes when researchers manipulated the magnetic field. The researchers then checked whether any structural changes had occurred in the ants' nervous systems. Our neuroanatomical analyses show that ants exposed to an altered magnetic field have smaller volumes and fewer synaptic complexes in the area of the brain responsible for the integration of visual information and learning, i.e. in the so-called mushroom body, explains Fleischmann. The analysis also showed structural changes in the part of the ant's brain ganglia that is responsible for spatial orientation. The ants that were allowed to make their first migrations in natural conditions clearly differed from the workers that took their first steps outside the anthill in a disturbed magnetic field. Their sensory experiences, combining information about the magnetic field, the position of the sun and the visual environment, triggered a learning process accompanied by structural changes in neurons and an increase in synaptic connections in the mentioned areas. Under normal circumstances, that is, when the magnetic field was not disturbed, the young ants showed an increased number of synaptic connections, places where neurons connect to each other. The authors of the study suggest that processing information from the magnetic field is not only about effective navigation, but also plays an important role in the development of spatial memory in ants. During educational walks, ants need a working magnetic compass to calibrate the visual compass and at the same time store images of the nest surroundings in their long-term memory, Fleischmann said. In the next step, the team wants to investigate which organ the ant uses to receive information about the magnetic field and through what sensory routes the information is transmitted and processed. This has not yet been achieved by any animal species that orients itself in the Earth's magnetic field.